In the magnetic resonance angiography, MRA, the image of the blood vessels is obtained using MRI techniques. In today's lecture, we will see the basic principles of this MRA. We'll also see the principles of functional MRI, fMRI. This fMRI is used for brain mapping research. Magnetic resonance angiography, MRA, is a technique for visualizing blood vessels. These images of blood vessels are used to diagnose abnormal narrowing, occlusions, dilated or ruptured vessel walls, and other abnormalities of the blood vessels. The flow or contrast effects on MR images are used in MRA. MRAs are divided into two categories: dark and bright blood MRAs. Dark blood MRA techniques suppress the signal from flowing blood while leaving the signal from stationary tissues unaffected, rendering the vessels black. The dark blood effect can be achieved by emphasizing flow-related defacing or taking advantage of blood's T1 and T2 properties. For the diagnosis of blood vessels, dark blood MRAs using FSE, IR, and SW techniques are now widely used. Non-contrast and contrast-enhanced MRAs are the two types of bright blood MRAs. Non-contrast MRA uses MR features of a flowing blood, such as an intrinsic relaxation times, time of flight, and spin phase effects to image blood vessels. The TOF, PC, SSFBP, FSE, and the ASL MRAs are some of the techniques used in this MRA. Contrast-enhanced MRA, on the other hand, uses MRI contrast agent to brighten regions of blood vessels in the MR image. As a result, this technique necessitates the fast injection of a gadolinium-based agent into a vein. The paramagnetic contrast agents then shorten the bright relaxation times, result in bright blood vessels on T1 weighted images than the surrounding region. This MRA images show bright blood MRA and dark blood MRA. In bright blood MRA, blood vessels are brighter than the surrounding tissues. On the other hand, in the dark blood MRA, blood vessels are dark compared to the other surrounding tissues. Now let's see the types of blood flow. First, let me see the laminar flow. Laminar flow is most normal blood vessels. The blood and most normal vessels, the blood flow is nominal flow. In nominal flow, the blood is a viscous fluid, so it has viscosity. Due to the viscosity, the blood flow has zero velocity at the blood vessel's walls. And this reason, the velocity of blood flow is zero. And reaches its maximum velocity in the middle of blood vessel, because viscosity is minimum at the center of the blood vessel. Near the blood vessel walls, there is the blood has viscosity due to this blood vessel walls, so the velocity of the blood is zero on the blood vessel walls, and here, and at the center of the blood vessel, viscosity is minimum there, so you can see the maximum velocity of blood flow. So this distribution of the blood velocity can be expressed by this equation. So here the average is half of the maximum at center of the blood vessel. So at the center, r equals 0, small r equals 0, so velocity of blood will be maximum. And at the walls of blood vessel, r equal small r equal large r, so we have the zero velocity. And this shows the prop flow. Prop flow is idealized type of flow. So everywhere the velocity of blood is the same, so constant. So this is not actually practical, but it's idealized type of flow. This figure shows the turbulence flow. There's some neck between two blood vessels. So neck is connected by two blood vessels, and then blood is flowing in this direction, and here we can obtain turbulence flow. So turbulence flow is abnormal vessels in this situation, because there are small lag between blood vessels, then we can obtain the turbulence flow. Blood components move randomly, so random motion here, so causing them to have different phases. Because of this, the MR signals cancel out one another, yielding no signal. at this turbulence flow. Next, this is flow separation. Blood vessels are divided into two vessels, so flow separation occurs. Near the walls of vessels, some of flow is separated from the main stream. For example, carotid artery is an example of the flow separation. Now let's see some effects of the flowing fluid, flowing blood. First, we can observe time of flight effects, TOF effects. But actually, there are two different types of opposing effects on the MR signals as a result of blood flow. The first one is flow voids, which are high velocity signal loss. The high velocity blood in the spinnaker pulse sequence is exposed by the 90-degree pulse, but escapes the image thickness before being exposed by the 180-degree pulse. As a result, the echo signal is not produced by the high velocity blood. So high velocity blood escaped the image thickness before being exposed by 180-degree pulse. So this high velocity blood does not produce echo signal. So this is called high velocity signal loss. The dark blood MRA can be produced with these flow voids. So we can use this flow voids to produce the dark blood MRA images. However, for the 180-degree pulse is not required in the GRE pulse sequence to replace the spins for echo signal. Thus, the spin echo pulse sequence is the only one where the flow void effects occur. So in the GRE pulse sequence, this high velocity signal loss does not occur, because in GRE pulse sequence we don't use 180-degree pulse to replace the spins. But in the spin echo pulse sequence, we have to use 90-degree pulse first, and then 100-degree pulse. The function of 100-degree pulse is to replace the spin. So we need two pulses, 900 and 180-degree pulse, to produce echo signal. So high velocity blood can escape the image thickness before being exposed by the 180-degree pulse. So this high velocity blood does not produce the signal, so we can have the high velocity signal loss. The opposing effects of the high velocity signal loss is the flow rate enhancement effect. So signal is increased due to this effect. Flow-related enhancement effect is the second effect of blood flow. The blood flow voice we discussed before in the previous slide. The flow voice opposite effect is the FRE effect, flow-related enhancement effect. Since the blood is not exposed by the pulse, the new blood entering the image thickness has the maximum longitudinal magnetization, that is saturated. Therefore, large signal can be obtained by the newly entering blood into the image thickness, because this longitudinal is switched to the transverse magnetization to give the signal. So entering new blood has its maximum longitudinal magnetization, and this maximum magnetization, longitudinal magnetization, is flipped to the transverse magnetization and detected as signal. So we can have large signal from the newly entering blood into the first image sequence. The GRE pulse sequence exhibits these FRE effects. As the GRE pulse sequence does not use 180-degree pulse and T is very short, as was already mentioned, there are no flow voice in the GRE pulse sequence. We already discussed this in the previous slide. The maximum FRE effects can be observed if new blood enters the image thickness during TR. As will be discussed in more depth below, the blood velocity for the FRE effects is significantly smaller than that for flow voice. This is due to the fact that whereas flow voice blood is related to TE, the FRE blood is related to TR, and TR is much larger than TE. This FRE effect allows us to create bright blood MRA. The blood flow inside the blood vessel causes it to appear brighter, whereas the other tissues outside the blood vessel do not experience the FRE effect. So we can get bright blood MRA. First, let's see the TOF loss flow voice in details. The spins exposed by both 90-degree and 180-degree pulses in the spin echo pulse sequence provides the echo signals. So the spins must be exposed by both 90-degree and 100-degree pulses to produce the echo signals. Yet, high velocity blood escapes the image thickness without being exposed by the 180-degree pulse. After 180-degree pulse, the echo signal is produced at the T over 2. Okay. So that's 90-degree pulse and the 180-degree pulse. Yeah. The time between two pulses is T over 2. and the echo signal appears TO2 after 180-degree pulse is on. Okay. So after 180-degree pulse, the echo signal is produced at the here at this moment. Okay. As a result, blood moving faster than this velocity, okay, escapes the image sequence delta G without being reviewed by the 180-degree pulse. Okay. The blood flow is similar to laminar flow, in which the blood's position determines its velocity. As a result, the blood vessel spins move at different speeds. The fraction of blood in the vessel that is not exposed by the 180-degree pulse is expressed as acceleration. Hence, this fraction affects the loss of TIF signal, which is blood voice. So this figure show how the blood exposed by 90-degree pulse, but not by 180-degree pulse. Two pulses, the time interval between two pulses, 90-degree and 180-degree pulse, and the signal, echo signal appear at the same time interval, half of t. So at t, at the moment t, the blood inside the image thickness delta G escapes. This image thickness after t plus t over 2, so the blood inside at this moment escapes after t over 2 time later escaped, right? So this blood velocity is given by this relation. Okay. So the high velocity blood escapes the image thickness before being exposed by 180-degree pulse. So the blood speed, if the blood speed is larger than this speed, then that blood escapes the image thickness before being exposed by the 180-degree pulse. Okay. Let's see some example here. In the case of delta G equal 1 centimeter, the image thickness is 1 centimeter, and t equal 50 milliseconds. Determine the minimum blood flow velocity to create to avoid signal loss. We have this relation. So put this value delta G 1 centimeter and the t equal 50 milliseconds. We can have 40 centimeters per second velocity of the blood flow to give the Bravais effects. The high blood velocity causes Bravais in the spinal cord sequence. But in the GRE pulse sequence, there are no Bravais because in the GRE pulse sequence, we do not use 180-degree pulse. Next, let's see the flow-related enhancement. The blood entering within the thickness of the image was not exposed by the pulse and has high level of modulation, producing a strong signal. Okay. The signals from stationary tissues are lower than those from incoming blood as a result of this effect of blood signal. So, the FRE effect, flow-related enhancement effect, also known as the entry phenomenon, is term given to this effect of newly entering blood. So this effect is due to newly entering blood. So this FRE effect is also called the entry phenomenon effect. If the blood flow is faster than this value, it will be able to enter the image thickness within TR. So blood flow velocity is larger than this velocity, then the blood will be able to enter the image thickness within TR. We have to obtain the MR signal within this time TR in the GRE pulse sequence. Unsaturated inflowing blood produces a strong signal in the GRE pulse sequence if the blood velocity criteria mentioned above is satisfied. As this relation is satisfied, the percentage of newly entered blood is indicated. So this condition indicates the percentage of newly entered blood. So this fraction affects the effects of FRE. Okay. This figure shows the FRE effect. Delta G is the image thickness, and at initial time t, blood is here, new blood is here, and after tr times later, this blood moves in the image thickness. Okay. So within TR, we check the MR signal. So if this blood enters during time TR, then we can get the MR signal from this blood, newly entering blood. So the condition of the blood velocity is given by this relation. So delta G is image thickness and the TR is pulse repetition time. So we check the MR imaging during this time TR, time interval TR. Let's see the example. Determine the minimum blood flow velocity to achieve the FRE effects in case of image thickness as 1 centimeter and the TL is 1000 millisecond. So using this equation, we can get blood velocity to give the FRE effect. Just 1 centimeter per second, very small. As a result, FRE effects can still be seen in low blood flow speed, like venous flow. Because of this, we can get the bright blood MRA using the GRE pulse sequence. This table shows the blood velocity in several different vessels. So this aorta, the velocity of the blood is very high, 150 to 175 centimeters per second. So very high speed flow. Arteries and the aorta speed is very fast. So this artery, the broad velocity is 40 to 70 or something, and in veins speed is small. We have small speed here. This slide gives the diameter of the vessel and the velocity of blood in that vessels. So if we enter aorta, diameter of the vessel is 2 centimeters and blood speed is 55. So this kind of artery blood flow, blood velocity is very high velocity, 70, 115, 90. Now let's see the spin phase effects. The spins in the blood flow move to a new location where the gradient fields are different from their previous location. So blood is flowing, and we have gradient field. Okay. So at first the blood was here, and the blood is flowing, it's moving. So at this moment, the spins in the blood feel this magnetic field, gradient field. But if the blood moves, for example, the blood is here, after some time later, then the magnetic field in this blood changed, right? So the spins at this position, the magnetic field, the spins experience is different from that in the previous position. So the position of the spins in the rod changes x equal pt in the case of constant rod speed v. So rod is moving with speed v, then the position of spins in the rod changes with a time t. So the position is changed to x equal vt. As a result, the position was changed, so the magnetic field, the spins field is changed. So Gx as there is a slope of the gradient, and x is position of the spins, the rod. Then we can have GVT as a gradient field there. So the position of the spins in the rod changes as x equal vt in the case of constant rod for v. As a result, Gx is changed. So at that position, in new position, gradient field is changed, xgvt. The spins in that location have a precession frequency of gamma v. So gamma v is now changed to v0 plus gvt. Okay. The phase change of the spins caused by the gradient field is obtained as this relation. So theta phase change is the integral of this angular velocity according to time. Then we can get this relation. The phase change depends on the square of times. Okay. If the Rameau frequency caused by static field gamma v0 is left out, so we don't have to consider this Rameau frequency due to the static field, because every tissues feel the same, the static field, so we can omit that in our discussion. So due to the movement of the blood, the nuclear spins in blood, the phase change is given by this relation. The phase change of this form is experienced by the spins in the blood moving at speed v of time t. The spins in the stationary tissue, on the other hand, are stationary and remain in the same gradient field g. Therefore, their phase change with respect to time t is thus denoted by gamma gt. So here we can see the difference between flowing blood and stationary tissue, the phase change. The phase change of the blood with the speed v is given by this relation. So the phase change depends on t square. However, the phase change in the stationary tissue is given by this form, gamma gt. So the spins in the stationary tissue, the phase change depends on just t. The spins in the flowing blood is given as this one. So the phase change depends on t square, but the spins in the stationary tissue phase change just depend on t. So there's difference between flowing blood and stationary tissue. As a result, it is clear that the phase change of the spins in flowing blood depends on t square, whereas spins in stationary tissue depends only on t. There's difference. We can tell the difference between stationary tissue and blood using this characteristic. The FE, flow encoding gradient with bipolar gradient structure, is used in PC, phase contrast MRA, to determine the velocity of the flow, blood flow, which varies depending on position. We will discuss this flow encoding gradient later in details. Two gradient fields. This FE consists of two gradient fields with opposite directions, but the same area make up the FE, this flow encoding gradients. While the spins in blood undergo a phase change proportional to their velocity, the spins in stationary tissue are not affected by this bipolar gradient. We will see this in detail next slide. The spins in flowing blood and the stationary tissues can be distinguished from one another using the different behaviors that they exhibit along the FE gradient. So we will discuss this in detail in below. So next, let's see the even echo rephasing. This is the effect of the actually phase difference between stationary and flowing blood. The odd echo dephasing and the even echo rephasing, odd echo dephasing and even echo rephasing that are seen in the successive spin echo pulse sequences are caused by spin phase effects of the spins in flowing blood. Whereas even echo rephasing obtains echo signals at the even number spin echo pulse sequences, the odd echo dephasing does not produce an echo signal at odd number spin echo pulse sequences. So this is called odd echo dephasing and even echo rephasing. The spins are rephased, then we can have MRI signal. But spins are dephased, then we cannot obtain the signal. So even echo or rephasing means at even number spin echo pulse sequences, we can obtain the MR signal. But odd echo rephasing means that at odd number of echo or spin echo pulse sequence, we cannot obtain the MR signal. As was previously demonstrated, the Rameau frequency with respect to time and the frequency encoding gradient Gx is given by omega equal gamma Gxbt for the spins in the flowing blood moving at the speed of v. As a result, we can calculate phase change between times t1 and t2 as follows, using this angular velocity. So phase change as angular frequency of t1 to t2, then we can have a phase change between 2 times t1 and t2 is given by this expression. And if you use this value k, then we can have this as a phase change between times t1 and t2. On the other hand, the phase change for spins in the stationary tissue of the same time interval, t1 and t2, is given by this form. So, in the flowing blood, the phase change depends on t square, but in the stationary tissue, phase change depends just t. Depends on just t. Now let's see what the even echo rephasing and odd echo or dephasing are. This is the phase equation in the previous slide. Okay. So we have the 90-degree pulse here and 100-degree pulse. So spin echo pulse sequence, and we successively apply 180-degree pulse to obtain the echo signal. So this is first, and the second, and third. So this is odd, right? That's even, odd. Now let's see the phase change using this relation. At this moment, phase is 0, so no phase change here. And then from here to here, the time between these two pulses is denoted by tau. Tau is TO2. Then this also tau, right? So 2 tau, 3 tau, and 4 tau, and 5 tau. So time is given by this form. And from here to here, time interval is tau, and the phase change of the spins in the flowing blood is given by this form. So 2kt dt 0 to tau. So we can have phase change k tau square. So here the spins in the flowing blood has phase change k tau square at this moment, but stationary spins just depends on time, so this change is given here. And at this moment, 180-degree pulse is applied, so k tau square becomes phase becomes minus k tau square due to this 180-degree pulse. Okay. And next, starting from here, the phase is changed. So this starting from k minus k tau square, and from here to here, so here tau, this 2 tau. So from tau to 2 tau to kt t dt. So we can have the phase change at this moment is 2k tau square. Okay. On the other hand, the spins in stationary tissue just depends on time t. So we have the straight slope like this, and at this moment phase, so no phase change, so phase is 0, so we can have the echo signal. However, the spins in the flowing blood has phase 2k tau square non-zero, so we cannot have echo signal from the spins in the flowing blood. So this is called the odd echo or signal loss. So odd echo or dephasing. So due to odd echo or dephasing, we cannot obtain echo signal from the spins in the flowing blood. For stationary spins, the phase is 0, so we can have the echo signal from the spins in the stationary tissues. Now let's go on. At this moment, here k2k tau square, starting from 2k tau square, and time is 2 tau to 3 tau, 2 tau to 3 tau. So integral gives 7k tau square. So at this moment, 7k tau square phase change here. Stationary spins has linear phase change, and at this moment, second 180-degree pulse is applied, and so this phase change will be change sign. So we have minus 7k tau square for stationary tissue, just at this moment, at this point. And now at this time, starting from minus 7k tau square, and time is 3 tau to 4 tau, 3 tau, 4 tau. So integral, then we have 0. So, and even is even 180 degree pulse. This odd. So 1, 2, 3. Right? So even echo. So even 180 degree pulse, the spins in the flowing blood, the phase is 0. So it gives the echo signal. So this is called even echo rephasing. Okay? So we can do same thing in third or fourth or other thing. So if you do this, then if you continue this, then we can see that for even for odd 180 degree pulse, we cannot obtain the echo signal, but for even 180 degree pulse, we can have echo signal from the spins of flowing blood. On the other hand, the spins in the stationary tissue always give the echo signal tau time after 180 degree pulse is applied. So that is called odd echo dephasing and even echo rephasing. Okay. Let's see here. When the echo signals are generated, the phase of the spins in the stationary tissues become 0 at each time. So tau, 2 tau, 4 tau. At this each time, stationary tissue gives the echo signal. As a result, at every step of spin echo pulse sequence process, we can obtain the echo signal of the spins in the stationary tissue. Okay? On the other hand, during the process of all the spin echo pulse sequences, the phase of the spins in the flowing blood does not become 0, as we already saw that. So odd echo signal. So we don't have odd echo signal, but we can have even echo signal, okay, from the spins of flowing blood. As a result, when processing every odd spin echo pulse sequencer, we are unable to obtain the echo signal from the spins in the flowing blood. Yet each time an even spin echo pulse sequence is processed, the spins in the flowing blood experience the phase change that equals to 0. So, with every even echo pulse sequence process, we can obtain echo signal. So this is called even echo rephasing. This called the this show the even echo rephasing. So the bright CSF region, we have bright signal, and here odd echo. So in the CSF, the blood flowing. Blood is flowing, so for odd echo signal, we don't have odd echo signal, but we can have even echo signal. This is odd echo signal, we don't have that. And here, even echo signal, we have the signal from the blood. Although historically significant, even echo rephasing is not used in the multiple spinal cord pulse sequences depicted above. Instead, the flow compensation gradient is applied to FAC and GRE pulse sequences to obtain bright blood MRA. We will discuss this flow compensation gradient in details later.